Yeah. First, I gave you this simple recursive function definition, and you told me it's not good. Yeah. Because, you do the computation, in some redundant way. Yeah. Not efficient way. Yeah. Next slide, we will see that. Next slide, I will draw a diagram to show you that. Yeah. All right. Yeah. So first, the answer is correct. Yeah. But the implementation is not efficient. Yeah. Yeah. So we're not satisfied with this implementation. Yeah. And I also mentioned the efficiency, the performance, growth function has the exponential growth. Yeah. All right, so the problem, yeah, so let me write write the main problem. Yeah. Yeah. All right, so the first implementation, why it is bad. Okay? Yeah. Yeah. Because its growth function has exponential growth. Yeah. Some of you may ask me, how do you see exponential growth? Yeah. We will see later. Yeah. At this point, we cannot see. Yeah. Yeah. Some people you can imagine, some kind of growth, but it's not that obvious. Yeah. But later, after we complete the Fibonacci formula, then we can see exponential growth. Yeah. Here we do not know the Fibonacci formula, right? So you may not know, what kind of exponential growth. Yeah. So this exponential growth rely on Fibonacci formula. Okay? Yeah, so we will see that soon. Yeah. All right. It is horrible implemented, right? Exponential growth, that's horrible. Okay? I said last time, any algorithm with exponential growth cannot be used in real world situation when the data size is relatively large. Only when data size is very small you can use. Yeah. Relatively large, you have to give up. Okay, you have to give up. Yeah. All right. Yeah, so here I want to draw a recursion tree to show you why this straightforward recurrence relation is not efficient. Yeah. Let's just use the simple Fibonacci number, Fibo of 6. We calculate the small Fibonacci number 6. We want to see how much redundant computation we do here. Yeah. All right. In order to calculate Fibo of 6, we need to calculate these two Fibo numbers, Fibo of 4 and 5. In order to calculate Fibo of 5, we need to calculate Fibo of 4 and Fibo of 3, and so on. Okay? Yeah. Now you can see the whole complete recursion tree looks like this. Yeah. That's the computation we need to calculate. If we use our previous slide that recursive function directly, yeah, we need to do a calculation like this. Yeah. That's not efficient. Yeah. Because you can see a lot of redundant calculation. Okay? Yeah. For example, how many times we calculate fiber of 2? Yeah. Let's see, the same number, why we need to calculate so many times? Yeah. The ideal calculation, we only need to calculate each fiber number once, right? Yeah. Other than one calculation for each fiber number, all other calculation, all redundant. So we should eliminate the redundant calculation to get an efficient algorithm. Yeah. So that's the problem here. Okay, yeah, all right. Too much redundant calculation here. You can imagine if the fiber number is very large, you can think about fiber of 100. The tree is very big. Yeah. Too much redundant calculation. Yeah. So we cannot take this one. Yeah. Oh, yeah. All right. Next, we want to improve this algorithm. How to improve the algorithm? Yeah. All right. Method 1, iterative algorithm. We do not do recursion. Okay. The first idea, because a lot of redundant computation is due to that recursion, due to the straightforward recursion. Straightforward. We didn't do the recursion right. If we do the recursion right, we won't have the redundant computation. Yeah. But the first method, we just avoid recursion. Yeah. We do iterative way, so then no redundant computation. That's the first solution. Yeah. How to do it? For loop without recursion, that's simple. Yeah? Yeah. So you calculate for loop. Yeah. Yeah. All right? So you create an array, F array. Yeah. Initial value, you have 2 initial values. And after 2 initial values, you calculate F array value 1 by 1. Okay? 2, 3, in the, we call this bottom-up way. So this is the bottom-up implementation. Okay, bottom-up. Yeah. Yeah. At the end, you reach the top. Okay, yeah. The top value, f of n. Yeah. But there is no redundant calculation. Each value we only calculate once. This one very fast. This one very fast. Yeah. No question. Okay? Yeah. All right. Can you see how fast, if we use asymptotic notation, can you see how fast it is by asymptotic notation? Yeah. For its efficiency, asymptotic notation. Efficiency. By asymptotic notation. You can use big theta of n. It's linear, okay? It's linear. Because, yeah, here, array, so we have array f of n, okay? Each f number we calculate once. So that's approximately n times, right? Not exact, but approximately, okay? Plus, minus some small number, okay? Yeah. And approximately n, so we can use big theta of n. Yeah. Very fast, linear. Yeah. The old bad one, exponential. So exponential, so old one, very bad, a to the nth, a some greater than 1 number. Exponential function. Later we will see this n number, this a. What is that a? Okay. Here just some a greater than 1. Not exponential. Okay? Yeah, all right. That's the first algorithm. But we also want to consider second one. Second algorithm. Second algorithm, our idea is like this. We don't want to drop the recursion. We still want to keep the recursion. We only want to eliminate redundancy. We keep the recursion by eliminating the redundancy. That's the second method. Yeah. But you may ask why we do that. Because the first method already very good, right? Iterative method, this big theta of n, so good. Why you consider the second method? Yeah. Actually, our second method is slightly worse than the first one. Slightly slower. Yeah, the difference is very small, but slightly slower because we need to do a little more work. The second one. Yeah. But it has its value. The second one, still important, useful. We keep the recursion because the reason is we know recursion has its biggest advantage. Recursion. Let me check. So if any student contact me. Yeah. Otherwise, I just turn off. Whatever. Yeah, let me just turn off. All right. Yeah. Yeah. So here, recursion. Yeah. So why we don't want to drop recursion? Yeah. So here, we know recursion has its biggest advantage. Biggest advantage is power. It's very powerful. If we throw away the recursion, we throw away its power. Okay? Problem-solving power. If you recall the Tower of Hanoi, think about if we do not use recursion, how can you solve it? Okay? So we don't want to throw away the recursion. Okay? Yeah. So we want to get a good, efficient algorithm but preserving this recursion idea, approach. Okay, yeah. So how to fix the problem? Yeah. Here, this idea is very important. Yeah. Here I use this chance to introduce you a very important algorithm, very useful in the real-world applications. Yeah. Here, let me describe this algorithm. Recursive algorithm without redundant computation. Yeah. How to do it? Yeah, think about. Yeah. We just modify our old bad algorithm slightly by removing the redundancy. Can you imagine how to do it? Yeah. We remove redundancy. Yeah. Yeah. We keep the old one. Yeah. Old one. So the question, how do you detect certain operation is redundant or not? If you can detect certain operation is redundant, then you can avoid it. If you cannot, then you cannot avoid it. Okay? So here we need some book tracking, bookkeeping approach, okay, to help us, identify if an operation is redundant or not. Okay? Yeah. Here, some careful bookkeeping strategy is important. Bookkeeping strategy. Bookkeeping for what? For our data. Bookkeeping our data is important. Okay? Keep track of what part of the Fibonacci numbers you already calculated. What part of the Fibonacci numbers you haven't calculated. Track of them. Okay? So then you can find an efficient way. Yeah, that's the idea. All right. Use an array to store calculated values. Yeah. Every time after we calculate certain Fibonacci numbers, we need to store in an array. Yeah. Store in an array. All right. Yeah. Make sure that no value is calculated more than once. The second time, if the same Fibonacci number, the second time you want to calculate, you have to stop. Okay? So you need to know if it is the first time you calculated or not. Can you imagine some simple, easy way to tell you if it is the first time you calculate certain Fibonacci number? Okay? Yeah, all right. Here, some important type of algorithms we call the dynamic programming idea in chapter 8. Here, this way, this method, we call it dynamic programming. Yeah. In this class, we do not have a chance to learn dynamic programming because it's an advanced topic. It's a graduate level topic. Yeah. But I can give you a simple introduction through Fibonacci number calculation. Give you a brief introduction. The idea is very important. Okay? Dynamic programming. Okay? So what's the dynamic programming? Yeah. How do we do dynamic programming? Yeah. We are at a situation we should apply dynamic programming here. Yeah. So let me explain the idea. Oh, sorry. Yeah. All right. The essence of this type of algorithm, no repeated calculation. That's what we need. Okay? Yep. But how do you avoid redundant calculation? Yeah. A bookkeeping method in dynamic programming, we call it dictionary method. Dictionary. How do you do bookkeeping? We create a dictionary to help us do the bookkeeping, data bookkeeping. Okay? All right. Yeah. Method 2, dynamic programming, dictionary method. We create a dictionary. So what's your dictionary? Just an array. So here, dictionary is a abstract concept. Yeah. It's not a real dictionary. Okay? Yeah. The dictionary, why we use this word dictionary? Because we want to look up our data in this storage place. Yeah. Certain storage location, yeah, buffer, temporary location, yeah. But we need to use this storage object for our data lookup in the dictionary. Okay, yeah, that's the reason people use this word. Yeah, all right. What's that? Array. We use array as the, dictionary. Okay, all right. Recursive algorithm without redundant computation. Yeah, using an array to store calculated value, and this array is the dictionary. We can do the lookup operations in this array. Yeah, all right. Make sure that no value calculated more than once. After we look up, if we can find it, then we do not do second calculation. If we cannot find it, that means it is not calculated, then we should do the first calculation. That idea. Okay, all right. Yeah. So here, this is the pseudocode. Here you can see pseudocode, we create an array, we use this name, known F. You can see the value stored in this array is known. The Fibonacci number value is known. So we call it known F. After you store it, that Fibonacci number is known. Okay? If you do not store it, that's the initial value 0. Because at the beginning, you initialize that array to 0. Okay? Yeah. So later, when you store a non-zero Fibonacci number, you change the value to non-zero. Then, every time you detect it, if it is known or not. If it's greater than 0, it is known, right? If it's greater than 0, this value is already available in the dictionary. So this is the dictionary, this array. You just return the value from the dictionary without calculation. How about that? So this return statement, you return the known value from the dictionary without calculation. So you save it. You save calculation. You just return directly. Okay? All right. If not, because if you return, then you get a value. You do not execute the remaining lines, right? After you return, you do not calculate the remaining lines. All right. When you go to the remaining lines, that means the value is not known. You need to do the calculation. Yeah. So two base cases. Yeah. Two base cases. Yeah. All right. Then this line, you do the calculation. Still recursive call. Yeah. You can do the recursive call. You don't worry, because these recursive call, most of them will use the known value. Okay? Yeah. Known value. No redundant calculation. So you don't worry about this recursive call. It only uses known values. It never calculates same Fibonacci number twice. Okay? All right. So then, after you get S, before you return, make sure you store it in your dictionary. Make it known. Store S at a known F of I, that location. It becomes known. After you calculate it once, it becomes known. You put it in the dictionary, so the next time you expand your dictionary, right? So next time, you just look up your data in your dictionary. If it is available, return it without calculation. If it's not available, do the calculation. That's simple. So this idea, we call it dynamic programming. Dynamic, definitely dynamic, right? So you do things dynamic way, okay? Yeah. Programming, what's the programming? Yeah. Programming, here the meaning of the programming, different from our coding programming, okay? Coding, we write our code, logic programming, no. Here, this programming, we use old meaning, okay, in history, old meaning. So it's called a table, okay? Programming means you organize your data in a table. That's the programming, okay? Yeah. Old meaning programming, okay? Yeah, old meaning programming. Yeah, table, yeah. Table, that's our dictionary. Dictionary and table, the same meaning. Tabular. People use table to organize the data. Here we use dictionary to organize the data. So table and dictionary refer to the same thing. Yeah. So dynamic programming. That's a brief, short introduction here. Okay? Yeah. So here, compare our method 2, method 1. Why method 2 is slightly slower than method 1? Because recursion, think about recursion when you use stack, right? There is a relatively deep stack. Deep stack, yeah. Okay? Yeah. The first method, iterative, we do not use stack, right? Iterative, you use temporary variables. You can reuse the same temporary variables again and again, right? So you don't need a stack. You don't need a deep stack. So the resource used for method 1 is significantly less than the resource used for method 2. Although they're both in big theta of m. Yeah. They're both in the same category, big theta of m, linear. Yeah. But the memory resource used quite different. Memory resource. Yeah. All right, so that's how much I want to say about the first round Fibonacci number calculation. The first round. Yeah. Algorithmically. We solve the problem algorithmically, the first round. Second round, mathematically. Mathematically. Okay? All right. To solve it mathematically, we need an important concept, quantity, here C.2, golden ratio. We need that. Golden ratio. Yeah, here. So let me introduce this golden ratio. Yeah. How to define golden ratio. Yeah. Here, because this golden ratio, this number is so special, yeah, it is closely related to painting, yeah, artists. So they, based on their experience, so they feel when they draw the painting, so when the scale of different parts of the body arranged following this golden ratio number, so then it looks perfect. Yeah, so that's what from the ancient people, based on the experience, yeah, from ancient people. Yeah. All right. Here, this, some way, yeah, here you can see this square, rectangular things, just to use the Fibonacci numbers in a, interesting way. Yeah. Here, you draw square with the size taking the Fibonacci numbers and see what happened. Okay, all right. 0, we pass the 0. Okay, the first one, 0. We start with the first non-zero Fibonacci number 1. Okay, let's draw a square with side 1. Yeah, yeah, look at that little one. Side 1. Okay, all right. Fibonacci number of 2, also side 1, right? So the second square also 1. Okay? So 1, 1. Yeah. So put together. Yeah. The next one, 1 plus 1 equals 2. So you draw square with side 2. Okay? So these 3 squares, you can pack them in a rectangle. In a perfect way, right? So it's a perfect way. Yeah. No extra part, exact rectangle shape. Yeah. Then you pack the next one. Yeah. Square with side 3, then you can fit them in a perfect way, yeah, and so on. Okay? Yeah. So then the next one. Every time you can add a new square with the next Fibonacci number as its side and join with all the previous squares to form a perfect rectangle. How about that? Okay? no extra material, okay? You need to cut, okay? Yeah. Put them together, align in a perfect way. Yeah. All right. Then, yeah, another way you can see, because for each square, you draw a quarter arc. So this is a quarter arc, okay? Quarter arc, okay? Yeah. So here, you can see, yeah. So here, the quarter arc, you draw different. So quarter arc here, quarter arc there, quarter arc there, yeah, here, okay? You draw each square, you draw quarter arc. Then you can connect, so you get this, beautiful spiral curve. Yeah. That's another way, So actually, there are many interesting properties people can derive related to Fibonacci numbers and the golden ratio. Yeah. Fibonacci and the number golden ratio closely related. Yeah. Closely related. So here you can see, Mona Lisa, yeah, all these figure shapes, you can see, you can find from that Mona Lisa painting. Yeah. All right. Yeah. But we need to define this golden ratio. How to define it? Yeah. Here, this is the golden ratio definition. Okay. Yeah. That's the formula to define it. Yeah. All right. Here, let me use my diagram to explain its definition and the derivation. Yeah. So the ancient people, the Greek ancient people, so they make the argument, based on their, real world experience. So, people realize, so they define this special number in some reasonable way. Yeah. So they feel reasonable way. Okay. Yeah. So they get two line segments, one longer, one shorter, A line segment, B line segment. Yeah. The length will be determined. Yeah. Determined based on some conditions. Yeah. All right. Then put them together, you have A plus B longer line segment. Here you can find three different line segments. A, B, A plus B. Okay. Yeah. Then they take the ratio of two line segments and they argue to make it a perfect ratio, it should be in this way to define some perfect ratio. So what's that? Okay. Longer line segment, the length of the longer line segment A over B, that's some number greater than 1, right? A over B, certain number greater than 1, okay? All right. Should be equal to another ratio greater than 1. Another ratio from what you can see here, greater than 1. So what's that? A plus B over A. Yeah. Because you want to get something greater than 1. So A plus B, longer line segment over slightly shorter line segment. That's B. That's A, not B. Okay. If it's B, the gap is too big, right? So over A, not over B. Okay, A plus B over B equals A over B. Yeah. So they argue, so this kind of ratio, if you can find AB line segments with the ratio in this way, that should be the perfect ratio. Okay? Yeah. All right. So now let's solve. What is that ratio? What is that A over B ratio? Okay? To solve it, let us write A plus B over A in this A plus B over A. Some simplification. Yeah. A plus B over A. Yeah. After we write in this way, you can see left hand A over B, right hand Y 1 plus B over A. You see something, these two fractions are closely related, right? What is their relationship? Two fractions. A over B and B over A. Some special relationship. Okay. Just reciprocal, right? B over A is the reciprocal of A over B. Okay? All right. Reciprocal, yeah. So if we represent A over B as one number, x, yeah, only one number, x, because here A and B, two different numbers. We want to simplify it. We use one number to represent the ratio, x. Then B over A is reciprocal of x. That's 1 over x. So you get an equation, x equals 1 plus 1 over x. That can be solved, right? Yeah. You have one equation and only one unknown. Why you cannot solve? Yeah. You can solve. Okay? Yeah. All right. So the ancient people, after they derived this single variable equation, they have confidence. They can solve it with huge confidence. Yeah. Just solve it. Yeah. All right. Yeah. So the equation can be simplified to this quadratic equation. X squared equals x plus 1. Quadratic equation. Yeah. So the next step, we want to solve this quadratic equation. Yeah. So let's apply the quadratic formula to find the solution. The standard form of the quadratic polynomial, ax squared plus bx plus c, a not equal to 0. Yeah. We know the quadratic formula gives us the x value can take two values. Yeah. Minus b plus minus, two values, 1 plus, 1 minus. Root of b squared minus 4ac, yeah. That's the numerator, denominator 2a. That is the two possible solutions for this quadratic equation. Yeah. All right. Our quadratic equation, the current one, x squared minus x minus 1, abc, a1, b minus 1, c minus 1. Let us plug in these abc values into this quadratic formula. After simplification, we have x may take two values, 1 plus or minus root 5 over 2. Two values. One is 1 plus root 5 over 2. Another is 1 minus root 5 over 2. But here, what's the meaning of x? Let's recall the meaning of x. Ratio of two line segments, right? Ratio, if we go back to the original meaning of x, equals ratio of two positive length line segments. So a should be greater than 0. X should be greater than 0. But 1 minus root 5 over 2, this number is less than 0, right? Yeah. 1 minus root 5 is negative. That means x cannot take negative number, right? Yeah. So if we interpret x as the ratio of two line segments, we should drop its negative value. So you can see, we don't take 1 minus root 5 over 2. Okay? So the answer is approximately equal to 1.618, yeah, but the exact expression is 1 plus root 5 over 2. That's the, so-called perfect number, perfect ratio, okay? Yeah, yeah. The golden ratio. Ancient people, they call it the golden ratio. Okay, all right. Yeah. Then, yeah, because this special number should have some interesting usage. Yeah. So people use a special Greek alphabet to represent it, phi. Similar to the way we use pi, right? Yeah. Another Greek famous alphabet approximately equal to, right? Yeah. Yeah. Pi, right? Yeah. Very famous. Yeah. This phi, not as famous as pi, but also, we can say second famous probably. Yeah. Second or third, because there is an E, very also famous, right? E constant. Yeah. Yeah. People can argue E probably more famous than phi. Yeah. 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 But these three, okay, yeah, very important constant. Yeah. Very important constant. Okay? All right? Yeah. So that's the, a little bit history, derivation of this special golden ratio number. In order to derive the Fibonacci formula, we need this golden ratio number, phi. Yeah. Here, let me give you the magic formula, okay? Yeah. Here, yeah, because, our ancestor, they derived this formula, okay? We just get from there, okay? Magic formula for the Fibonacci number. Why magic? Because it's hard to understand. Why the formula looks like this? Very hard to understand, comprehend this formula, okay? Yeah, let me give you that. Yeah. Yeah. So we can appreciate the power of math. Yeah. F sub n, the n Fibonacci number equals 1 over root 5, parenthesis, then inside, parenthesis, phi to the nth, phi golden ratio, minus a fraction, minus 1, negative 1 to the nth over phi to the nth. So here you can see why we feel, people feel hard to comprehend. Yeah. Because root 5 is an irrational number, right? Root 5. So, we cannot say it's a good number, easy to handle. Yeah. Not easy. At a denominator, root 5, not easy to handle. Okay? All right. So then, inside the parenthesis, phi, it's another irrational number, right? Yeah. Phi, 1 plus root 5 over 2. Another irrational number. Another number with a lot of digits, Yeah. It's not easy to represent accurately. Phi raised to nth power. Okay? Also, very hard to control. Okay? What's that? Hard to control. Yeah. Then minus some fraction, phi to the n at the denominator, That you take the operations, subtraction first, then division, then you get an integer Fibonacci number, integer. How can that possible? How can these things be possible? Okay? Yeah. 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 The Fibonacci number. Yeah. Yeah. All right? Yeah. So. Yeah. So this is the formula. But we need to prove it. Or we need to verify it. Why this special expression gives us Fibonacci numbers, all Fibonacci numbers. We want to see it. Okay? Yeah. All right. Yeah. Right. Question. How can you connect the Fibonacci numbers to the golden ratio? In part D, we will see the connection. The connection, natural connection through this equation. Because they can be connected with the same equation here. That equation. Okay? Yeah. All right. Yeah. Yeah, we will see that. All right. So now we finish part C. Yeah. And then let's move to part D. Part D, we will work on Fibonacci formulas. Yeah. All right. Oh, so I clicked the wrong thing. Yeah. Should not be end show. I want to change the pen color. All right. Part D, Fibonacci formula and the linear recurrence relation. Yeah. This part we need to do a lot of math. Yeah. Yeah. Some students, feel, too much math. Yeah. Yeah. But in algorithm class, at certain locations, certain situations, we have to do quite a lot of math. Yeah. But not all the time. Okay? Yeah. Some special situations, we need to do some math. Yeah. 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 All right. So actually, I treat this algorithm class typically 50% math, 50% computer science. Yeah. We rely on math a lot. Yeah. Logic thinking, all the analysis, details, you need to use math tools to do it. Yeah. Yeah. But computer science, the other half. Yeah. Implementation, coding efficiency, all those things. Yeah. Computer science. Yeah. All right. D.1, verify Fibonacci formula. Here we only do special case verifications. Yeah. We divide it into two parts. Yeah. The first part, special case verification. Second part, general case verification. Yeah. And here, I mentioned before, I will apply mathematical induction. The first time in that binary representation one, I skip it. Okay? Mathematical induction, that place to prove the formula, the general case formula, I skip it. But here, I do not skip. We need to do mathematical induction only once here in this class. In our notes, we only do once. In our homework question, not the first homework, the second homework, you have a chance to do another time, mathematical induction. Okay? Yeah. All right. So here the idea is important. Yeah. You need to at least to know this mathematical induction, the procedure to apply it. Yeah. It is very powerful. Yeah. So here, mathematical induction. All right? Mathematical induction, you need to verify a few special cases as the base cases. Okay? After that, you do induction. You make induction assumption, then after induction assumption, then you do some critical step to extend your induction assumption. Yeah, so you will see it. Yeah. All right. How to show that Fibonacci number can be represented in this formula correctly. Yeah. For all n, okay? For all non-negative integer n. How to do it? Not easy, right? Not easy. But in this topic, D.1, we only need to verify a few relatively small n values. That should not be hard, right? Yeah. Verify a few relatively small n number. Yeah. All right, so let's do the verification. Verification, the first step, when n equals 0, it's easy. Yeah. Yeah. Original f value, f0 equals 0. You have it. Then you plug it into this formula, 0, because phi to the 0, that's 1. 1 over 1, also 1. 1 minus 1, 0. 0 times 1 over root 5, also 0. Okay? So the first number verification, very simple. All right. Second, slightly harder, but not too hard, so we can still do it. Yeah. All right. F1, this time we need to calculate phi to the first plus 1 over phi. Yeah. Let's, put phi numbers there. 1 plus root 5 over 2. Yeah. The second one, 2 over 1 plus root 5. Yeah. When we see the fraction like this, the denominator is an irrational number. We have a standard technique. We can simplify it. Okay? Yeah. So basically, we just multiply, here. We multiply root 5 minus 1, root 5 minus 1, same number, both numerator, denominator. After simplification, we can get this number. Okay? Root 5 minus 1 over 2. Yeah. Because here denominator is 4. 4 and 2, you cancel out 2, you have 2 left. Yeah. So then, numerator, you only have root 5 minus 1. Yeah. All right. These two numbers, you add them up. All right. Yeah. Positive 1, negative 1 cancel out. Root 5, you have 2 root 5. 2 root 5 and the 2 cancel out. Root 5 cancel out. So you have 1. Yeah. So the value is 1 here. Okay? Yeah. So you verify the second Fibonacci number, F1 equals 1. Yeah. All right. Then the third one becomes a little harder. Yeah. Third one. Yeah. For our mathematical induction, we do not need to do the third one. Yeah. But here, I want to show you some algebra technique. So I try a few more verification. Yeah. Here, the third one, we need to calculate phi squared and 1 over phi squared. Yeah. All right. Yeah. So the phi square, this one, 1 over phi square, we calculate from the previous one. That's 1 over phi. we take square, so we have that. Okay? Yeah. Then we expand these numbers and we can do cancellation. What cancellation we can do? 1 and 1 here, 5 and this 5 cancel out. Yeah. So then 2 root 5 plus 2 root 5, that's 4 root 5. 4 cancel out, root 5 left. Then root 5 and the outside root 5 cancel out, I have 1. So f of 2 equals 1, another verification. Okay? Yeah. Not too bad. Yeah. It looks like we can handle it. Yeah. Not too messy. Yeah. Yeah. All right. Then the next one, I want to verify another one, although not necessary. Yeah. For mathematical induction, already enough. Yeah. Yeah. But next one, I want to show you a new approach. Yeah. We have 10 minutes. Yeah. All right. Our last verification. Yeah. That's the last one, number 4. F of 3. F sub 3 this time. Phi cube plus 1 over phi cube. Yeah. All right. Here, I don't want to do expansion way. Okay? Yeah. Although I can handle, yeah, but I want to show you a special way that people do the simplification with properties of the golden ratio. Here we apply properties of the golden ratio. Yeah. So what are the properties of golden ratio? Yeah. So let's look at the properties of golden ratio. Okay. So here, degree too high, phi cube, yeah, in our calculation, we feel too high, how to calculate directly. So we want to find a way to bring down the degree. Bring down the degree to make it simpler. Yeah. Not that high. Yeah. Bring down. Yeah. But how to reduce the degree of phi cube? Reduce the degree. We apply the properties of golden ratio. What are the properties of golden ratio? Yeah. Look at, there are 2 properties we can use here. Okay? The one property, first property, 1 equals phi squared minus phi. How to see that? Phi squared minus phi. Okay? Second property, phi squared equals phi plus 1. Okay? All right. Remember, how do we calculate phi? From quadratic equation x minus 1 equals 0. Original quadratic equation for golden ratio phi, if we plug in phi, it should be equality, right? Yeah. Phi squared minus phi minus 1 equals 0. From this identity for phi, can you get the first property? You move 1, minus 1 to the other side, you get a 1 equals phi squared minus phi. Okay? Yeah. You move minus phi minus 1 to the other side, you get a phi squared equals phi plus 1. Okay? Yeah. So these 2 properties can help us reduce the degree of phi cube in calculation. Okay? Now let me show you how to bring down the degree by applying these 2 properties. Okay? All right. Yeah, here, I just repeat the story a little bit. Yeah. Now let's calculate phi cube. We split phi cube as phi times phi squared. Yeah. When you see this phi squared, can you apply the second property? Replace phi squared by phi plus 1. Yeah. All right. Then you multiply through equals phi squared plus phi. You see another phi squared, right? Can you replace this phi squared by another phi plus 1? You can. So you get a 2 phi plus 1. Now you bring down the degree, right? Yeah. Original phi expression, degree is 3. The new expression, degree is 1. Much lower than the original one. Okay? All right. Yeah. Then let's look at 1 over phi cubed. We also want to bring down the degree of the denominator, phi cubed. This time, bring down degree of denominator. Yeah. All right. How to do it? Yeah. Apply properties of golden ratio. Yeah. All right. The first time property, numerator is 1. Can we apply the first property of numerator, of golden ratio? 1 equals phi minus phi. Okay? If we replace 1 by phi squared minus phi, there is a common factor between numerator and denominator. Common factor. Okay? Phi is the common factor. We can do cancellation. Right? Yeah. After cancellation, numerator becomes phi minus 1, denominator phi squared. So we bring down a little bit. Okay? All right. Now you see minus 1, that 1. Can you apply the first property another time? When you see 1, yeah. So you replace 1 by phi squared minus phi, parenthesis. After simplification, you get 2 phi minus phi squared, numerator, over denominator phi squared. You have another common factor phi between numerator and denominator. Okay? So 2 over phi minus 1. Now the denominator, the degree, becomes much smaller, right? Phi. The denominator, the degree of the denominator only first order. Now, these two expressions looks simple enough, so we can add them up and see what do we get. Add up these two expressions, we get 2 times, because negative 1, positive 1 cancel out. We factor 2 out, 2 times phi plus 1 over phi. This one we calculated before, right? Yeah. We add root 5, so we get F3 equals 2F1. That's 2. Okay? F3 equals 2. That's the same as our computation result. Yeah. So in this example, we verified n equals 3 case. Yeah. I want to use this example to show you how to apply the two properties of golden ratio to do the calculation. Different. Yeah. Sometimes you need to use this way to do the simplification related to the golden ratio. Okay? Yeah. That's enough. So we don't need more practice. Yeah. That's all we need. Yeah. All right. Next, we need to go to D.2, verify Fibonacci. Oh, why another special case? Yeah, this should be wrong. This should be the general case. General. General we treat it as one case. Okay? Just general. Yeah. All right. Now, mathematical induction. Yeah. So let me just do some short introduction. Yeah. So then we will do the, major verification work next time. Yeah. Verify the Fibonacci formula. Here we need to use the powerful mathematical induction tool. Yeah. All right. So we need to review a little bit. In mathematical induction, first we need to verify base cases. So 1, we check the base cases. we did it in D.1. We completed the base case checking D.1. Yeah. Here we only need to check F0 and F1, but we do more than necessary, right? After F1, we also did F2 and F3. Yeah. Yeah. Here we can check as practice. Yeah. Yeah. But not necessary. For mathematical induction, we don't need these two. Yeah. Yeah. Step 2, mathematical induction. Yeah. Mathematical induction. Mathematical assumption. Yeah. Yeah. Assume that the formula is true for 2 less than equal to k less than equal to m. We assume that. Yeah. 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 Next time I will explain why it makes sense. Yeah. Today we don't have that much time. Okay? Yeah. All right. So we make this assumption. Then the step 3, we verify that for n plus 1, this formula is correct. That's the standard procedure of mathematical induction. Yeah. But next time, when we come back, first I want to explain why this method makes sense. Why we need to, following this procedure, we can prove the formula is correct for all non-negative n numbers. Yeah. Then we do the verification. Okay? Yeah. All right. Yeah. So let's stop right here. Yeah. Next time we will finish. Yeah. After we finish, next time we can do some review. Okay? After we finish this topic, we finish module 3. Yeah. So we can do some review. Okay? All right. Review, so I can talk about quiz questions. Yeah. Quiz 1, quiz 2, quiz questions. Yeah. All right. Yeah, that's it. Yeah.